Today, I would like to introduce our latest achievements obtained in our promoting research on the supercomputer Fugaku, which is entitled as Direct Digital Transformation of the Manufacturing Process and Smart Design in the Society 5.0 era. To begin with, I would like to talk about the Society 5.0. This is a society following the hunting, agriculture, industry, and information societies. This concept is advocated by Japanese government as a future society that Japan should aspire to. It is a society that balances economic advancement with the resolutions of social problems by a system that highly integrated cyber and physical spaces. Currently, we are now in the information society where we access a cloud service or a database in cyberspace via internet and search for, retrieve, and analyze the information or data by ourselves. In Society 5.0, a huge amount of information from sensors in physical space is accumulated in the cyberspace, and this big data is analyzed by AI, and the analysis results are fed back to us in the physical space in various forms. In our team at RIKEN R-CCS, we are seeking for new digital engineering to be realized in the Society 5.0. There, the cyberspace is integratedly combined to physical space, where the industrial design and the manufacturing actually take place. There are some examples we are now trying to develop on the Fugaku platform. On your left, for example, when we provide necessary engineering performance together with styling or shape preference to meet both engineers and stylists' requirements, multi-objective optimizations coupled with high precision simulation is automatically executed. And AI proposed some candidate styles meeting the provided performance and preferences. On your right is a sort of the digital twins, providing on-road conditions, providing on-road driving and the surrounding environmental data. Many high fidelity simulations together with virtual drivers are executed simultaneously, and the AI suggests the best driving operation depending on the driving condition. Then what sort of a software should be developed to realize such a digital engineering in the Society 5.0? Firstly, we have to deal with a huge number of simulations at very high speed, including the both pre and post processing. Secondly, simulation should be not only high precision, but also a sort of the tailor-made to realize real digital twin by precisely reproducing each product shape and considering the enormous real-world conditions. Unfortunately, current engineering simulation framework based on the unstructured mesh system does not meet these requirements. Firstly, a huge amount of the workload is required for the pre-processing of calculations shown in the pie chart here. This figure shows the turnaround time for a conventional vehicle aerodynamics CFD in industry in hours. Typically, 8 times longer time is necessary for the pre-processing compared with the simulation itself. This is because of the data cleaning requirement to make a watertight surface for the unstructured mesh system. Secondly, unstructured data fundamentally have difficulty in tuning on new hardware architectures because of the irregular memory access. There are the various ways to improve calculations efficiency by serializing data access or the utilizing cache reusability, but it tends to be a memory access bounding. So in our team, we also develop and support the unstructured CFD called front flow rate HPC. After some tuning on the Fugaku, still its single node performance is less than 3%, and its parallel performance in weak scaling is about 40% on the only 500 nodes. So we fundamentally changed the data structures from the unstructured to the hierarchically structured grid, considering its application to HPC on massively parallel environment. Here, we adopted the hierarchically Cartesian grid as the basis of the grid system. The basic data structure is similar to that used in the adaptive mesh refinement, having two fixed levels of subdivided spatial domains. The computational space is first divided into cube, which are going to be a double as they approach the walls of the geometry. Cube is divided into cells, typically a 16 by 16 by 16 assigned in our simulations. Since each cube is composed of the same number of cells, it is easy to evenly distribute the computational load to each processors. So it is advantageous for achieving high degrees of parallelizations. The software is called Cube, having been developed in our team since 2012 as a complex unified simulation framework on massively parallel environment. In this framework, we solve multiple partial differential equations on the same hierarchically structured data. For example, unified continuum mechanics equations adopted for both fluid and structure motions. Thus, Cube is very effective against strongly coupled fluid structure interactions, which is difficult to achieve high performance on massively parallel for the conventional frameworks on the massively parallel environments. Cube already has many achievements on the flagship supercomputers like K and Fugaku. On your left is a direct feedback noise predictions emitted from a small gap of a real road vehicle, and the combustion international engine simulations on your middle. On your right is this is a very new result. It's a ski jumping simulations of gold medalist Kobayashi Ryoyukun and its comparisons with the jumpers by realizing the whole body pose change from the takeoff to landing, and explaining why his jumping is superior to other jumpers. Regarding the single node performance of the cube of the Fugaku, we can achieve about 6.39% against the theoretical values, and it is about 200 gigaflops, which is about 2.4 times faster than the Xeon Phi-based system. Still, we have a room for the improvement, and now we are trying to improve this performance up to 9% by utilizing the memory access serializations, loop collapse, loop fissions, and the array dimensions exchange. Regarding the parallel performance, on your left, when the target is very similar cavity flows, up to 27,000 nodes, we could achieve the 4.5 petaflops, which is equivalent to 4.9% of the peak, and its scaling is 21%. This is it's a weak scaling. And on your right is a real vehicle cases. We use a hierarchical structured grid and up to 51,000 nodes and scaling with 74%. So our code so far can treat more than the tens of the billions of meshes on the cube. So we could realize world's largest vehicle aerodynamics simulations as shown here. But actually, these types of high fidelity simulation, high precision simulation is not so popular in the automotive industry because of the considerations of the cost of required for these simulations, and they are much more interested in the capacity computing. On the other hand, the disadvantage of the method is a treatment of the wall in the fixed block mesh. In this framework, we take advantage of this shortcoming by adopting the immersed boundary method to reproduce a solid surface. Still, there is a problem of the accuracy near the wall remaining in our simulations. The advantage of our improved immersed boundary method is its very fast mesh generations without modifications of original digital CAD data. Regarding the immersed boundary method, so far, most of the existing method can be categorized into two main streams. One is a peg-skin method. The other is a metered method. Anyways, in both two methods requires identifications of solid and fluid part. In our new immersed boundary method, we abandoned this idea. So in this method, it is a sort of the enhanced method of these two methods, adopting the ideas of dummy cells for wall, including the cells. It enables us to specify the solid cell fully arbitrarily in the virtual space. Then even the wall having the zero thickness and or gaps or overlaps typically observed in the real CAD data, it can be modeled without any restrictions of the geometrical topologies. And as a result of that, by this novel immersed boundary method, we could speed up the pre-processing, including CAD cleanup by the 100 times to 1,000 times faster than the conventional unstructured CFD method. Hereafter, we would like to introduce some of our achievements using this framework on Fugaku. The first one is multi-objective optimizations of road vehicle shape, utilizing the genetic algorithms called Cheetah developed at Jackson. Here, we set up the four objective functions relating to the crosswind stability, and the fuel consumption rate. The aerodynamic performance of each vehicle shape was evaluated by the high precision CFD simulations, and the entire optimization process was executed fully automatically on Fugaku. The idea adopted here is we developed a surrogate model. We developed a surrogate model by AI technique utilizing the CFD results as a training data, which are obtained at earlier stage of the optimizations. And by reproducing a part of the performance evaluations with this surrogate model, the cost is almost free. So we have succeeded in reducing cost while ensuring the optimization accuracy. These two figures indicate the comparisons of the case. Whole process is conducted by simulations with mixing of the simulations and surrogate model. And two typical vehicle shapes obtained by these optimizations are indicated here. The above is this result. This is high crosswind stability vehicles. It's the lowest. I mean that it's highest crosswind stability vehicles, even though the drag is somehow larger. On the other hand, this one is a lowest emission car. It's a lowest drag, while its crosswind stability is quite worse. Anyway, these are the shapes provided by the AI. The second example is a digital twin simulations realized by coupling the vehicle aerodynamic simulations and the vehicle's multi-body simulations, reproducing the vehicle's body to 6 degrees of free motions as well as the suspension system. The aim of this simulation is to evaluate the drivability of a vehicle. For the drivability evaluations, a very small change of the model must be reproduced as phase-free as possible, as shown here. This is because the drivers are quite sensitive to the difference of the body shape. So this framework can treat the very detailed vehicles geometry. It is almost the same as the real vehicles. And on your left is a case. On your left is a lane change maneuvering without turbulence. On your right is a lane change, lane change maneuvering, but reproducing with atmospheric turbulence. And we are investigating how these types of the turbulence affect the road vehicles' performance. Not only the pose of change of the vehicles, but you can also obtain the steering input imposed by the drivers riding on this vehicle. The COVID-19 pandemic occurred early 2020 when we are tuning cube on Fugaku. So we soon noticed that our simulation model for the internal combustion engine and fuel injection model implemented on cube can be utilized to simulate the droplet and the aerosol for dispersions for the infection risk evaluations. This is a sort of the digital transformations of the airborne transmission risk assessment. And this figure indicates the number of daily positives of COVID-19 in Japan, together with some of our simulation results. For 20 months, we have treated over 50 social infection scenes and conducted over 1,000 cases for the risk evaluations and proposal of countermeasures. Until now, we have consumed about 220 million node hours of Fugaku. And this is only because the very fast mesh generation. This can be realized thanks to the cube's very fast mesh generation system. As you may notice that our droplet dispersion simulations only predict the transmissions of droplet emitted from the infected persons and how much droplets are inhaled by the person at risk. After that, we adopted a very rough probability model to predict the infection risk based on the epidemiological assumptions. To make our predictions more reliable, we have to investigate our simulations with more microscopic risk assessments based on the bioregulation model, together with a more precise human body and respiratory tract numerical models. So this is one of the examples of our current simulations of host cell dynamics coupled with a numerical respiratory tract. Virus lagging drop particles that reach the blessing zones are transported from the neurus into the upper respiratory ways and partly are deposited on the inner wall, and some of them transported to the lower respiratory tract. There is a clear correlation between the airway depositions and particle size, and the fine particles of 100 nanometer or less are well deposited in the airway wall due to the effect of Brownian diffusions. And similarly, the particles larger than the 1 micrometer diameter deposit well in the upper respiratory ways due to the gravitational settling effect. The deposited virus-laden particles on the mucus are transported in the directions of the larynx by mucocilium motions, as shown here. At the same time, the virus infects the host cells and begins to replicate. At the time series of the change in number of target susceptible cells, infected cells, and viral RNA copies are obtained by solving the simple host cell dynamics model shown here. And this is obtained results. In these analytical conditions, assuming COVID-19 infection, 2 days. The 2 days after the inhalations of virus-laden particles, the droplets, the virus concentrations exceeded the detection limit of PCR test and peaked 5 days after the infections. I think I'm running out of my time. I'd like to stop my talk here. Thank you very much.